Hello, good evening, everybody. I'm sorry for the slight technical issue that we've had. Started going live and we realised that the picture wasn't visible, so we had to turn that off. So hopefully you'll be able to find your way over to this alternative stream on the Facebook channel. I can see that a couple of you are already joining us over here, and I think we'll just wait a few minutes to allow other people to gather as well, which should be great. These technical things are going to happen in these early days of us learning our way around this new technology. So I'm joined this evening by Dr Bethan Davies. Hello, Bethan. Nice to see you.
Hello, Al. Hi. How are you?
Yeah, very well, thank you. As I was just saying to hopefully the folks watching at home, we'll just wait a few minutes to allow people to gather. Of course, this is being recorded anyway, so we can always share this with on Facebook and, of course, on the YouTube channel afterwards as well. I'm just going to check and see how many people have moved over to join us here. I don't know if you're monitoring this as well, Bethan. We've got a couple of people watching at the moment, and hopefully the numbers will gather as we move through. So as I say, everybody, hello, welcome to the third of our live question and answer sessions in the Department of Geography's Geography for Schools lectures here at Royal Holloway. As many of you will have seen, Bethan gave an absolutely fantastic lecture on glaciers and the subject of mass balance last week, and this is now an opportunity to talk to Bethan about that subject, but also more generally about studying glaciers and what it's like to be a glaciologist at university. And I know that some of you have been asking questions over the past week, and I'll try and feed those questions to Bethan during the lecture. But I wondered if we might just start, Bethan. Could you just give us, perhaps for those who have a short memory or those who weren't able to catch up with your lecture last week, could you just give us a brief summary of the main issues that you were talking about last week, if you'd be so kind?
Sure. So in my lecture last week, I talked about glaciers. And a glacier is essentially a pile of ice. Every year, snow falls on the glacier in layers, and if that snow doesn't all melt in the summer, eventually you'll grow a glacier. It's just a pile of compressed snow. And that compressed snow is actually a viscous liquid, a sticky, slow-moving liquid. I don't know if you've ever played with oobleck or kinetic sand or anything like that, if any of you are perhaps teachers with children, but a glacier will move just like that oobleck or that kinetic sand. So glaciers will flow downslope under the force of gravity. And as a glacier flows downslope under the force of gravity, it gets warmer because it gets warmer as we move towards sea level. Anybody who's hiked up a mountain knows that it gets colder towards the top of the mountain. And as you move further down the glacier, it will start to melt because it's warmer. So when you have a glacier, it tends to be dominated by processes of snowfall in the upper part of the glacier and dominated by processes of snow melt in the lower part of the glacier. So that part of the upper glacier that mostly receives more snow than is melting, we call that the accumulation zone, because that's where the glacier is accumulating snow and ice. And then that lower part we call the ablation zone, because that's where you get more ablation, where you get more processes of glacier melt. We call the balance between these two processes mass balance. And you can think of it a little bit like your bank account. You have processes of snow and ice coming in, and then you have processes of snow and ice melting or going out. If you have your bank account and you get paid in monthly, but you don't spend very much, then your bank account will grow. Whereas if you spend more than you earn, then over time your bank account will shrink. Glaciers are very similar. If over time they receive more snow than they lose by melting, then the glacier will grow. Whereas if they melt more than they receive in snowfall, then the glacier will shrink, and over time it will become smaller. It will still always flow down slope, but you get more melting as the climate warms and the glaciers shrink. worldwide, we currently see glaciers shrinking all across the world. In almost every part of the world, glaciers are shrinking. They're currently contributing almost 2 millimeters a year from Antarctica, from Greenland, and from glaciers to global sea level rise. Almost 2 millimeters every year. These ice masses worldwide are being affected by climate change. So as the climate's warming, we're getting more melting for these glaciers, and we're seeing that pattern worldwide. And the other thing that I talked about in my lecture was that glaciers are actually a critical water resource for around a third of the world's population. These people live downstream of these glaciers. And what glaciers do, which is really helpful, is that they melt in the dry season. So in places with very seasonal snowfall, like the northern Andes or the Himalaya, the glaciers produce meltwater in that dry season, which people use for irrigation, for domestic consumption, for hydropower, and for industry. As glaciers worldwide are shrinking, they're putting pressure on those water resources, making water shortages more likely in the future.
Bethan, thanks so much. That's a brilliant summary of of last week's lecture, and I think you've painted a vivid picture of the changing nature of glaciers in the 21st century, but also, of course, the human reliance on glaciers. So I'd like to try and unpick some of those issues with you as we go through the lecture, and certainly some of the questions that came in were absolutely on those topics as well. Can I just start then with the metaphor that you used of the bank account, because certainly my bank account at the moment feels as though there's more coming out than there is going in. So my bank account's very much in the ablation zone. Can you just tell us, obviously in the past there has been this process of accumulation, and in the past glaciers have got bigger. They have grown to the extent that they are today, and indeed they've obviously been much bigger than they are today. So what is it that's changing? Have we apparently reached this tipping point, and now glaciers seem to be becoming smaller than they perhaps had been in the 18th, 19th and early 20th centuries?
Yeah, well, so we can reconstruct how big the glaciers were at various times in the past. So when glaciers form a stable position, when they're in equilibrium with climate, they form a moraine, which is a landform at the edge of the glacier. So because the glaciers are continuously moving downslope and bringing debris with them, if they're in equilibrium with the climate and neither growing nor shrinking, they will build up a big pile of debris at the end, and that's a moraine. And we know how old those moraines are, because if they're quite recent, we can maybe date them with archival satellite imagery, or we can date them from topographic maps or from explorers' logs, or we can do clever things like measure the size of lichens on boulders, or count the tree rings for trees growing on moraines. And getting back further in time, we can estimate how long rocks have been exposed to cosmic radiation from outer space on these moraines. And so we have a wide number of tools that helps us calculate how old these moraines are. And what we know is that glaciers are now shrinking faster than they have at any point since the Little Ice Age maximum. So Little Ice Age reached its maximum around 1750, 1800, different times in different parts of the world, largely driven by changes in solar radiation, sunspot activity. Glaciers grew, and in the European Alps, glaciers reached their biggest extent during this Little Ice Age than they have for the last 10,000 years. In other parts of the world, the Little Ice Age extent is less pronounced, but it's very pronounced in Europe. But we now know from looking at glacier extent on an annual to decadal resolution, we can calculate rates of recession. We know that glaciers are now shrinking faster than they have ever done before. So they're shrinking faster than they were in the 70s. They're shrinking faster than they were in the 80s. They're shrinking faster than they were in the early 2000s. So we know that this is not an ongoing response to the Industrial Revolution at the end of the Little Ice Age. Glaciers are now shrinking ever faster, and every year the amount of water they contribute to sea level rise, which is a way in which we measure global glacier melt, is increasing. And this is largely driven by changes in global carbon dioxide. This is driving warmer summers, and that's increasing glacier melt. It's also changing precipitation patterns. So the local balance between temperature and precipitation is varied in different mountain regions, but universally, these glaciers are melting more and shrinking faster each year.
Okay, so this isn't just a steady decline in glaciers. What you're saying is there's an acceleration in their decline that we can trace back to the 1780s. There's been an incremental increase in the speed of decline.
Indeed, yeah. So we're seeing glaciers shrinking. And some of the work that I've been doing in Patagonia shows that glaciers are shrinking now at a rate that's faster than any point in the last 10,000 years. So not just the last 200, the last 10,000 years. And that's due to some very detailed work across the whole ice field, looking at these moraines and glacier extents over a longer period of time. That gives us a very long perspective to tell us that this behaviour is unusual. And the World Glacier Monitoring Service uses the word unprecedented.
Okay, so there's so much in this that we need to really unpack, and I think part of that is understanding the evidence that you can gather in order to make these kinds of important kind of claims and observations. Now, you mentioned some really interesting sounding techniques before that of the kind of things that frankly I hadn't ever thought about before. So, of course, at school I studied moraines. This was part of what we did, but I never really saw that as actually part of lively scientific evidence to be able to measure the extent of a glacier's former life. But because it was just a feature that we had to study, we had to be able to recognize them on a map. But what you're saying is that if you can identify the location of a moraine and you can attach it to a particular glacier, you're able to effectively map the history of that glacier, and you know the extent that it reached to, and therefore you can also calculate the rate of decline of the glacier today.
Yeah, I mean, moraines can give us a huge amount of information. A moraine is directly related to paleoclimate. So if you have a land terminating glacier that doesn't do anything complicated like terminating a lake or anything like that, you have a land terminating glacier, then your moraine is directly related to paleoclimate. And in fact, temperature and precipitation, it is directly related to temperature and precipitation. If you know one, then you can calculate the other. There's an empirical relationship. So if we have a moraine and we have it dated in time, that tells us how big the glacier was at that time. If we have an independent temperature record, say for example from an ice core, then we can work out how much precipitation there was. We can calculate the mass balance of the glacier. And we can say that at this point in time, the glacier was this big. And now we can date glaciers well back for the last few 100,000 years. And we can say, when the carbon dioxide was this, the glacier was here. When the carbon dioxide was this, the glacier was here. When carbon dioxide was falling and temperatures were rising, the glaciers were in this position. In some parts of the world, in the northern hemisphere, it was approximately similar temperatures to today during the last 5,000 years. The previous climatic optimum was kind of similar to today, so we can look at what the glaciers were doing there and use that as an analogue for where our glaciers might be in the future. So a moraine is a sensitive indicator of past climate.
And then you have just honestly transformed my understanding of moraines, because I'm sure, like many people watching from home, they are studying being able to identify what a moraine is. They probably know how it's formed. This is what the GCSE and the A-level, and I did the Scottish system. This is what the system teaches you. But I don't think we're ever taught about how these things can be helpful to glacial and climatic science.
Indeed, and they're so exciting.
This is absolutely wonderful. And then not only that, but the things that then can grow on moraines can also add extra evidence for the analogues that you're referring to. So you mentioned trees before. So a tree growing in a moraine, clearly it can only grow on there after the moraine has formed and the glacier has retreated. So that can also be a secondary indication, can it, about the changing life of the glacier?
In parts of the world where trees grow next to glaciers, they can provide us with lots of information. So say, for example, there was a period of time in the last 5,000-10,000 years where climate was quite pleasant and trees were growing in front of the glacier. The glacier may then advance as it gets colder during the Little Ice Age, pick up those trees and shove them in a moraine. So you get a moraine stuffed full with dead trees. This has happened a lot in places like Alaska. We can then radiocarbon date those trees and work out when the trees died. So we can have trees within the moraine, they're part of the sediment that we can radiocarbon date and say, at this time, the glacier was less advanced, and then we can date the trees growing today on the moraine. So we have a date for the moraine. So we can say when the moraine was formed, and then we can say when the trees died. And that tells us about glacier minimum extents as well as glacier maximum extents. So trees are fantastically useful.
This is very exciting. Now, you also mentioned rocks before, and the exciting term cosmic radiation. I think
yes.
You said cosmic radiation. So rocks, like everything else, are absorbing the sun's energy, and presumably they give something of that energy back over time.
Yeah, it's not the sun. It's supernova explosions from outer space.
Oh gosh.
And we are being...
You're literally taking us out of this world
out of this world, yep. We are being radiated all the time by cosmic rays from outer space. They're from supernova explosions really far away. And in fact, if you've ever seen the Northern Lights, mm-hmm. they are these cosmic rays being guided around the Earth's magnetic field. So there is a visual representation of these cosmic rays. And these cosmic rays...
So rocks have been subject to exactly the same kind of forces as our atmosphere is when we see the Northern Lights, the Aurora Borealis.
Indeed, yeah.
And how do we use that information?
Well, so these are really high energy particles. They're tiny subatomic particles, and they've got lots of energy. When they collide with certain atoms, they actually cause a little nuclear reaction. So when one of these high energy particles from outer space collides with an oxygen atom in something like quartz, which is silicon oxide, it splits the oxygen atom apart, and it forms a new isotope called beryllium. And beryllium doesn't occur naturally in quartz. This is only formed, beryllium-10 is only formed in this way, by the interaction of oxygen atoms with cosmic rays. So if you count how many beryllium atoms you have in a gram of quartz, and you know the rate at which they're produced, you know how long the rock has sat in that position.
That's extraordinary. So what branch of science is that called? Does that have a particular name?
Cosmogenic nuclear dating is widely applied in the geosciences.
Okay.
And it interacts with physics and chemistry as well. So it's all part of part of the sciences.
I sound like a complete novice here, but I genuinely had no idea that this kind of stuff was happening. I mean, I've heard of luminescence before. Is luminescence different to this?
Yes, luminescence is the time of burial.
I see.
So luminescence dating is rather different. Say your glacier has a river flowing away from it, and the river has lots of sand in it. That river will deposit the sand. The quartz grains in the sand will accumulate electrons. These are free-floating electrons, and they're more associated with radioactive particles in the sand itself, like zircons. And it's similar. You know the production rate, and you know... if you know the production rate, then you can take the quartz from that sand and you can work out how long it's been buried for. And we can use the two together. So you may have a moraine with some nice boulders on, with a sandy bar from a river behind it, and you could date it by both mechanisms and have a really well dated moraine.
Okay, so you would never really use one of these devices on their own. You triangulate and you cross-reference between multiple different sources.
We will use both. We'll use them on their own. It depends very much on the environment.
Okay.
There are so many ways in which we can date moraines, many, tens of ways, and they're all different, and so we use them in different places. So, for example, there's no point trying to radiocarbon date trees in Antarctica, because there are no trees in Antarctica. That method does not work well.
Lots of penguins, no trees.
Yeah.
Yeah.
Penguins, yes. Trees, yes. Trees, no. And penguins are difficult as well because they're marine organisms, and so their radiocarbon age is older than their actual age. So that makes it difficult as well.
Gosh. That's one for the family quiz at Christmas, isn't it?
Yeah, if you went to Antarctica today and you bopped a penguin on the head and radiocarbon dated it,
Yeah.
it would tell you it was about 1,300 years old.
No, you have to. I mean, I think we're going slightly down a kind of wormhole here, but you need to just tell us why that is. Why is a penguin 1,300 years old?
All marine organisms around Antarctica have an older radiocarbon age. And in fact, all marine organisms worldwide have an older radiocarbon age. And that's because there is old carbon in the ocean. Okay. So there is so deep old ocean currents circulating around the world, and they have old carbon. In the global average offset between the marine radiocarbon age and the terrestrial age is 400 years. That is the global average. Antarctica has a lot of very old upwelling water, and so it has a larger offset.
So this is purely in Antarctica. This doesn't really refer to other oceanic regimes around the world.
Anywhere where you get big upwelling, like the Pacific coast of Chile, you'll get an older radiocarbon age.
Oh, really? So if you are a keen swimmer and you've occupied the waters a long time on the coast of Chile, I mean, as chilly as it would be, I'm sure. But
depends how much water you swallowed.
Oh, it requires you to swallow the water, so not just being bathed in it.
Yeah, to make it part of your body.
Oh, I see. Okay, less appealing, I think. Okay. Oh, this is fascinating. Now, you also mentioned other kind of sources of intel about glaciers. So I think we've looked quite far back in time, but equally. Maps and as you say, explorers' reports. I mean, are these something that form part of your work? Because that strikes me as being very kind of human geography, which of course is something I'm far more used to.
Yes, it is. It's very much something that people do. So it's coming up to 200 years since the discovery of Antarctica at the moment, and people have used those very first ship's logs and ship sketches to reconstruct the Antarctic ice front 200 years ago.
Well,
I've been working in Patagonia, and we used Charles Darwin's logs himself because he went on a voyage around southern Patagonia, and he made fantastic observations of the glaciers, very detailed, and we can read them today and we go, oh yes, that's where the ice margin was.
That's right. I mean, what my area of research, as you know, at least in part, is in the Falkland Islands, and Darwin was in the Falkland Islands at some point during his Patagonian exploration. So this was part of that, and those observations that he made back in the 1820s, 1830s, something along those lines. Those have actually allowed modern day glaciologists, or they've given an insight into the glacial extent of some of the Patagonian glaciers. So it's still actively contributing to science, well beyond evolution, which is what it's most famous for.
Absolutely. Yeah, absolutely. And they do really interesting things. Like, we know that, for example, the extent of some of the large glaciers in Patagonia was quite small around 1750 due to explorers describing the glaciers, very distinctive glaciers that you could access by ship. And so we know that they were smaller, and then we know that they were larger by later explorers describing them again, and they described them so accurately we can pinpoint the ice margin.
This is really interesting, because of course there was also the birth of kind of scientific drawing and sketching at the time as well, wasn't there? So, and people were becoming far more accustomed to drawing in particular ways. So presumably those kind of drawings can also become a reference point, particularly if they involve distinctive landscape features, so you can trace again extents of glaciers.
Yes, indeed. If they draw a particular mountain ridge or something like that, we can use it. You may have seen in the news recently, there was a hot air balloon flight over Mer de Glace in France in, I forget exactly the year, around 1820, something like that. And that was recently repeated to compare the two surveys. And the original survey from 1820 told us where the ice was in that year.
Amazing. So those kind of what might have seemed quite incidental observations at the time have become really important and central to contemporary glacial science. Now, one of the issues that Ian Candy talked about in his Q&A a few weeks ago was the extent to which kind of glacial loss, and therefore that loss of white reflective cover, can then also lead to further environmental and climatic change. Can you maybe just kind of re-emphasize the point that Ian was trying to make a few weeks ago?
Yeah, I mean, one of the observations we've noticed about climate change is that it's warming much more rapidly at the North Pole and the South Pole than it is in some of the other parts of the world. And we call that polar amplification. So it's warming at a faster rate at higher latitudes. And this is down to a variety of factors, but one of the key ones is that as the glaciers shrink and the snow shrinks, the accumulation area shrinks, there's more dark material that absorbs more energy and then radiates it out. And then that is contributing to rapid warming. So, for example, the Arctic Ocean is a great big dark blue ocean. It's normally covered in bright white ice, but the Arctic sea ice is decreasing every year in spatial coverage. And that means that we have more dark blue ocean visible to the sun, and that's absorbing the sun's energy and warming very quickly. In places like Greenland, the area of snowfall over the summer in Greenland is shrinking. And that means that we have more glacier ice visible. And glacier ice is a dark grey and not like the bright white of snow. And so it changes the reflectivity, or what we would call the albedo of the glacier ice. And that means that it warms more.
I'm glad that you said albedo, because I had that name ringing in my head from years and years ago, and I couldn't quite remember what it meant, but I seem to remember that it referred to something to do with reflectivity.
Yeah.
So the higher the albedo, the more reflective the material is. Is that right?
That's right. That's right. Yeah, and snow is very reflective, and we know this because it's shiny and crystalline and bright. And when you see runners after a race, they'll often be wrapped up in shiny silver blankets to keep them warm, because it reflects the heat back into them. And it's the same with snow; it reflects the heat back up to space.
I see. So once that reflective white coating on the top of a glacier goes, so the fresh snowfall, the darker greyer ice that is then exposed when that snow melts, it absorbs more of the sun's energy, therefore melts more quickly, and therefore there's a natural accelerant effect in that process.
Indeed. Yeah.
Okay, so you've helped us establish something about the way that glaciologists work, which is, for me, absolutely fascinating. We've talked a little bit about albedo. What about the nature of different places in the world? So you mentioned the Antarctic and the Arctic. What about somewhere that you talked about in your lecture, the Himalaya? So there's presumably this glacial loss, much like elsewhere in the world. But what are the implications that you were identifying in your lecture from that glacial loss? Because, of course, one of human resource. They're not just a natural phenomenon. They're something that people rely on, just like we rely on reservoirs or kind of water towers, in the middle of the American prairie, for example. Why is it helpful to think about glaciers in that kind of slightly anthropomorphized kind of way?
People have anthropomorphized mountain regions since time itself. We have the mountain gods. Mountains produce water. So mountains are big and high, and any air flowing over these mountains is forced to rise. As the air rises, it cools, and precipitation condenses and falls on the mountain. So mountains themselves produce water. And because it's cold in mountain regions, that water is locked up in the glaciers. So it's stored in the glaciers. You can think of the snowpack and the glacier ice as a reservoir of water, a frozen reservoir, which then melts in the ablation season. And in the dry season, or even more pronounced in a drought year, that glacier ice provides a buffer. So it stops the stream flow from dying away completely. And it means that in places where you might not get very much rainfall in certain times of the year, you still get water in the streams and the rivers. And in places like Switzerland, that water is used for hydropower. In large parts of the downstream areas of the Himalaya, it's used for hydropower and is extensively for irrigation. And in fact, 250 million people live downstream of the Himalaya and depend on this water for irrigation, for hydropower. And as these glaciers shrink, their ability to buffer in dry seasons, and particularly in drought years, is much smaller. And we can think about this in terms of peak water. So if your glacier starts to shrink, it melts more each year. And that means that the stream flow may increase. And it's a boom time. You can irrigate more crops, you can plant more avocados, you can irrigate your paddy fields. So that's good. But eventually your glacier becomes so small that it is no longer able to produce as much meltwater. And so the stream flow decreases. And in the Himalaya, that timing of peak water is scheduled to fall between somewhere like 2030 and 2050 AD. So in the next 10 to 20 years, the stream flow will start to decrease and become smaller.
And what was the figure? Just remind us again of the number of people who are dependent on those Himalayan water sources.
250 million people in the Tarim Basin. And worldwide, 1.9 billion people live in downstream areas, downstream of these glaciarized mountains, and depend on these water resources.
So that's 250 million people effectively who live in, for example, northern India.
In the Tarim Basin, yeah.
Yeah. So that's a really terrifying prospect, isn't it? Because obviously these are people who do rely on water presumably for fresh water for daily life, but also for farming and for irrigation. And
extensively for irrigation, yeah. And this is an area with hydropolitical tension and intergovernmental tension. And this drainage boundary is transnational, so it crosses national boundaries. And I mean, this is geopolitics, which is your area, not mine. Yeah,
that's what I'm thinking.
And maybe you would like to comment on what a water shortage in one country due to damming of the river may mean for the downstream areas. But it is likely that we will see increased tension as the water becomes a more precious resource.
Well, I mean, and of course, to segue slightly into the geopolitical for a moment, I mean, there are very active border tensions between India and China and Pakistan right now, with all kinds of allegations of potentially China using new kinds of weapons against Indian soldiers high up in the Himalayas, because of exactly the kind of border conflicts that water shortages and the misappropriation of cross-border water supplies can have. So I think it's a really interesting segue from glaciology into geopolitics.
Yes, and it just goes to show how relevant glaciology is worldwide and what an important subject it is to study.
Absolutely. Now, on the subject of studying glaciers, you've clearly worked extensively around the world. You have an amazing track record of working in some exciting places. And I know that one of those places is Antarctica. And I think a lot of people are just generally intrigued about what it's like to work with glaciers. How do you do it? How do you prepare yourself for it? How did you get to Antarctica, for example?
Okay.
Tell us more.
So I'll answer the first question first, which is how do we get to Antarctica? And as a British person, I went to Antarctica with the British Antarctic Survey. We were funded by our Natural Environment Research Council, the UK government, so we went with BAS. And there are two ways that BAS goes to Antarctica, and I've been privileged enough to go with both ways. You can go by ship, and you can go by ship from the Falkland Islands or from somewhere like Ushuaia in southern Chile. So I've been to the Falkland Islands a few times now and departed there on the ship to go and sail across the Drake Passage to get to places like the northern Antarctic Peninsula. And the other way that people get to Antarctica is by aeroplane, and you can fly over the Drake Passage and go straight to one of our research bases where they have a runway, and Rothera is one of the British bases that's closest, and that has two runways. It has a gravel runway, which is kept snow-free all year, and an ice runway. And the skis there, the planes there can land on skis, and you can fly and land on the gravel runway and then go on a plane on skis and go off somewhere else. So that's pretty special. I have to say, flying to Antarctica is much more comfortable than going across the Drake Passage, because that is quite a challenging journey on a ship. The seas are extremely rough, and even though I had copious amounts of seasickness pills, I was very, very seasick.
I can only imagine. Having seen some of the fairly mountainous seas, even close to the Falkland Islands, I don't even like to think what it's like, further out into the South Atlantic there.
Yeah.
And how long do you go for when you go to Antarctica? Because I think most of us assume that you have to be there almost for a whole season. Is that right? Or can you go for shorter visits than that?
Well, a person like myself who studies moraines, I really need to be able to see the moraines. So I want to go when the snow is at the minimum. So I go to Antarctica in the summer, just for the summer. There are other people who go to Antarctica for a whole year. So people who study perhaps climate or biology, they may go for a whole year. But I'm a summer person, so I go there for the summer. But it still takes 2 weeks to get to Antarctica, because you have to build in quite a lot of contingency. It takes maybe 4 days to cross the Drake Passage, takes maybe 2 days to get to the Falkland Islands, and then you need a few days contingency either way. So it takes a good 2 days to get to Antarctica. And you have to bear in mind that the ships are very expensive. They're doing a large amount of science, but they have a large number of science teams that need the time on the ship. And there's a very complicated Gantt chart somewhere about which ship is going where, and you just have to fit in with that schedule, which can mean waiting for your passageway in various places.
It sounds quite exciting. I'm not going to lie to you. I mean, it must be pretty chilly, but incredibly exciting getting there for the first time.
There is nothing like seeing your first iceberg. Thinking, wow.
From the air or from the sea.
Yeah, the journey never gets old.
Yeah, absolutely amazing. Now, you mentioned an organisation called the British Antarctic Survey, and I wondered, could you just maybe again share with us a little bit more about BAS and the work that they do?
Well, BAS was set up really after the Second World War. BAS maintained several bases in Antarctica within the British Antarctic Territory, and they provide world-class research into Antarctic climate, Antarctic biology, Antarctic oceanography, as well as logistical support for other scientists who want to go to Antarctica. And maintaining this presence, this British presence in Antarctica. So they are extremely experienced. They have several royal research vessels which have drilling rigs so they can do deep ocean coring, and they have these amazing little submarines called autosubs, which are these clever little submarines that can go underneath the ice, floating ice. And all
That's
sorts.
not Boaty McBoatface, is it?
That is Boaty McBoatface.
That is Boaty, finally.
Yeah. And Boaty McBoatface is an extremely clever little submarine. And it can go underneath the ice all by itself. You can't have access to it because it can't receive communications under the ice. It has to be completely autonomous and find its way back again. Amazing. And occasionally they get lost in a crevasse or something under the ice. Which is
never to be recovered? No. Oh dear, all right. And that's an expensive loss on one of those days.
Yeah.
Yeah. So tell me, what's it like then working on a glacier? Can you describe the kind of work that you're doing?
Yeah, so
or on the moraines.
So some of my seasons, they all involve remote deep field work. So I am deep field, which means I'm not in a base, I'm in a tent, and I'm hundreds of miles away from anyone else. So for example, when I was on James Ross Island, I was in a tent for 7 weeks, and we were about 200 miles away from Rothera. So we were really, really on our own. We have a daily radio broadcast. So we have this big radio every day at 7 o'clock. We radio into Rothera, and they tell us the gossip on the base. They tell us the weather. But most importantly, they ask us if our carbon dioxide monitor is working. That is the most important question, because we cook in the tents, and carbon monoxide poisoning is the most dangerous thing that we face in Antarctica. It's not getting cold, it's poisoning yourself by cooking in your tent that is the most dangerous thing. So, so we have these carbon monoxide monitors. You spend most of your time making water. There is hardly any fresh water, so you have to melt water. All the time you're awake and in your tent, you're melting water. So the stove is going pretty much all the time, and you'll have a bag of freshly cut blocks of snow in your door, and you'll put them in the stove. Any water that you make, it will freeze overnight. So you heat that water up, and then you put it in a water bottle, and then you put it in your sleeping bag, and that gives you a nice hot water bottle, and it stops it melting, because any water left out will freeze overnight and destroy your bottle.
And then that water is at body temperature the next morning for you to use in
make your porridge with.
Oh, gosh, these are the kind of practicalities that you just don't really think about.
Yeah, water is the most precious resource when you're deep field. There is no running water to waste, really. All the water, even if you are making water all the time, you're awake and in base, you will only just have enough to eat and drink.
Okay. Not
any spare for anything else. So you will get up in the morning, melt water, make tea, melt some more water, make porridge, melt some more water, have another cup of tea, and then go out for the day. And as soon as you come back, you'll melt water for tea, melt water for a drink, melt water for your dinner.
And tell us about that work that you go out and do during the day. I mean, obviously you have the specialism in moraines. So what does your research life down in Antarctica look like? What are the things you're looking for?
Mostly I am looking for boulders, because I'm interested in dating how long those boulders have been exposed to these cosmic rays. So I'm mostly looking for a nice granite boulder on a moraine. And I'll have a pretty good idea about where I'll find them, because I'll have looked at satellite images before I go, and I'll have them in the field with me. And I have to go and sample them. When I was on James Ross Island, we had quad bikes, which enabled us to drive all over the island on these quad bikes. That was excellent. They do not work well in snow, so you have to go around the snow. And when I was on Alexander Island, that was an Antarctic specially protected area, and so we were not allowed any motorised vehicles at all, and we had to man-haul all our kit from where we were deployed from the aeroplane to our camp, and then walk everywhere, carrying a sledge across the snow.
Gosh, so I don't know that designation. So who has designated parts of Antarctica under that special environmental status?
The Scientific Committee for Antarctic Research will designate key areas that have a particularly unique geology or biology or ecology as Antarctic specially protected areas, and then it's very difficult to get access to them. You need to have a very good reason to go.
Right.
So you need to have a good scientific reason, really, to be allowed to go to an Antarctic specially protected area.
Okay.
And there are many more rules, like we couldn't have a generator, we couldn't have a skidoo, we couldn't have a quad bike. We had to be deployed quite far away and walk in. So it's very protected.
But that's still in what we would think of as British Antarctic territory?
Yes. Yeah.
Okay. And all of your work has been conducted in the kind of the British claimed zone so far?
Yes, all of my work's been with the British Antarctic Survey in British Antarctic territory. So all of it's been on the Antarctic Peninsula. Sure.
And of course, there's another whole interesting geopolitical conversation to be had around the claimants to Antarctica, but I think that's probably, we should save that for another time. And I know you've spoken extensively about that with my colleague, Professor Clive Dodds, recently in another podcast.
Indeed, yes.
That people can see online.
Feel free to look it up.
Absolutely, look it up. We'll put a link under this post to make sure that people have that. So you talked about gathering samples from these massive granite boulders. What does a granite sample look like, and how do you take a sample away if that's what indeed you have to do?
Yeah, we need 1 kilo of rock, and I strongly recommend a team to do this, preferably very strong right arms. You can do this very quickly with a rock saw, which is like what you might see someone using when they cut up your road to lay a new pipe or something. But that leaves a very big scar on the rock. And so that is not a very good way of doing it, because it leaves a very visible evidence that you've been there, which is not good in an Antarctic especially protected area. So I prefer to sample with a hammer and chisel, which is much more time consuming and much more difficult, physically much more difficult, but environmentally speaking, much less damaging. We're only really interested in the top couple of centimetres, so we'll spend a period of time chipping away at the rock to gather the top few centimetres. That rock, we need 1 kilo of that rock, which we then haul back to our tent, put it in a rock box and ship back to the UK.
Okay, so when you say a rock box, is that like a large metal chest or something like that?
A wooden crate about that big by about that big, and it is a British Antarctic Survey special box for rocks that we put our samples in.
So you Antarctica, what you're relying on, you're there to gather.
Catch that.
I'm sorry, I don't know if you could hear. When you're in Antarctica, you're gathering samples. You can't really process any of those samples when you're there. That relies on you taking them back to the UK, presumably, and to one of our labs here at Royal Holloway or somewhere else around the world to provide you with the data that you need. Oh. I think, Bethan, we've lost your audio. Can you hear me, Bethan? Hello, Bethan.
Can you say that again?
Can you hear me? Can you hear me? Hello. Come in. We've lost connection. I wonder what's happened here.
I can tell you a little bit about what we do in the field. I think that was what you were asking. So we spend our time in the field really, we can't phone home, we can't do anything else. All we can do is science. So we will spend our time mapping the landforms that we can find. We'll have a handheld global positioning system that will tell us our latitude and our longitude, and we will physically map the moraines and the features we can see, describe the sediments that helps us understand how they were made, and collect as many samples of granite boulders as we can. So maybe we'll collect 50 or 60 or 70 in a season. Each rock will maybe take 1 day, possibly 2 days to sample. So it's a huge undertaking. Those samples are then shipped back to the UK. All the time we're there, we're living on ration boxes. So we have to eat whatever's in the ration box. I think I was extremely excited to discover my field assistant had smuggled a packet of digestive biscuits in one year. I can hear you again now.
Oh, you can hear me. You can hear me laughing at the digestive biscuits. I hope they were dark chocolate. They're my particular favourites.
They were. I don't know what chocolate they were, but they were extremely welcome.
Good.
After eating biscuits brown for weeks and dehydrated peas.
Oh, biscuits brown. So you have military ration packs, do you?
Very much so.
Oh, okay.
Yeah.
So the question I was asking when we temporarily lost sound was, it's more, so you're gathering these samples when you're in Antarctica, but you don't really know what those samples are going to tell you because you can't do any of the processing work while you're there. That relies on you then having everything shipped back or flown back to the UK. And presumably over the months, potentially even years afterwards, that's when you do the processing work. So it's a real, it's a kind of real speculation, isn't it? You just don't know what those rocks are going to tell you for potentially a very long time after you're actually there.
Absolutely. Yeah, you've hit the nail on the head. We don't necessarily know we're in the field exactly what we're looking at. So the key, and being a good scientist, the key is very detailed observations. Good rationale for sampling, very detailed observations, and then when we get our ages back from the lab, from these exposure ages of how old these rocks have been on the Earth's surface, we can relate that back to our observations and our geomorphological map, and then we can write up the data set. But the processing these rock samples is very complicated and requires using some very nasty acids, so we send them off to a lab to do that for us.
Okay. Because I'm sitting pretty close to our labs here in the geography department right now. So we don't do that kind of stuff here. And that speaks to the exciting network nature of science, that actually you have to use different labs who have access to different techniques.
Yeah, these samples go off to a lab in Glasgow, East Kilbride in Glasgow. There's a national facility there. So you have to apply to a committee and ask for funding for your samples, and then send them off to, if you're accepted, if your samples are deemed worthy, then you send them off to Glasgow.
And in terms of the sharing of this information, Bethan, does this all add to some kind of national database of scientific data from Antarctica? How does that work? What's the share? Is there a sharing nature here?
All publicly funded research will be published open access, and the full data set will be made publicly available. So all the data is publicly accessible, and it's in various repositories that people can access and find. I think the challenge is actually there's an awful lot of metadata that goes with them that's quite complicated. And so periodically what will happen is that there will be a large community effort to review all of that data. So I was involved in a consortium of maybe 50 authors back in 2014, and we reviewed all the published ages by every paper, by every team across the whole of Antarctica. And we published this large meta-analysis of all the data to produce the most coherent new data set of what Antarctica has done, what the ice in Antarctica has done over the last 25,000 years.
And so, my first question is, and I'm just conscious of the time, and people I hope are enjoying the conversation. Is that just that big review that you did? Is that just stuff from the British Antarctic Territory, or is that from all scientific endeavours, from Chilean, Argentine, elsewhere? This
was an international collaboration coordinated by the SCAR, which is the Scientific Committee for Antarctic Research, and it was a hugely international effort led by people from different countries. Lots of people were involved in coordinating this, so this was very much an international effort.
Amazing. Now, I think we'll move on to the last phase of this, because I know one of your other great passions is about communication. About the Antarctic Glaciers website that you've been absolutely instrumental over recent years in putting together, because it's such a wonderful resource for people to have access to.
Oh, thanks. Yeah, so I set up Antarctic Glaciers quite a while ago now, back in about 2012, because I saw a gap, and there was just nothing like it online that was free and accessible and up to date and written by experts. And there was quite a lot of other websites that were perhaps disputing climate change and things, and there was not really an answer from the scientific community. And I thought, well, there's a huge gap here that we can fill. And so I've been working ever since then to write this website, and it really functions a bit like an online textbook now. It's completely free, and there's no advertising on it, and it's funded by scientific organisations, charitable grants. And it covers a huge range of topics. There's layered content on there. So there is content specifically aimed at A-level students, and that is flagged as such. And we are currently working with the Antarctic Science Foundation, have funded this fantastic new project where we're making some resources for younger students as well. And they'll be fully interactive, and it was always free and publicly available forever.
Amazing. I have to say, I've been browsing that a lot over the past week to ready myself for this, and it's a really super resource, and it's antarcticglaciers.org. Is that right?
That's right. Yeah.
So I think, and again, we'll put the link to that underneath this video to make sure that people can have access to that. Super. Bethan, thank you very much. Is there anything I haven't asked you? Because I'm aware that I could have left a horrible, terrible hole at the heart of this conversation, and I wouldn't want people to go away not knowing everything they need to know.
No, it's all excellent.
That's wonderful. Bethan, thank you so much for everything that you do, also for communicating science, but also for ask those in the comments under this video on the Facebook or YouTube channel, and we'll check them from time to time and make sure that people get answers to the questions that they have.
Absolutely.
Amazing. Bethan, thanks ever so much. And to everybody at home, thank you very much for watching. Now, as I mentioned, this was the third of the Q&As that we have this particular season before Christmas. And I just want to bring up this final little advert to advertise Professor David Gilbert's lecture and then question and answer session coming up on the 7th of December for the lecture, and then the live Q&A on the 14th of December. And David, again, will be talking on a subject that's really relevant to the A-level curriculum. He will be talking about changing places, relationships, connections, meaning and representation. So a kind of far cry from the world of glaciers, but nonetheless incredibly relevant, timely and important if you are indeed studying A-level geography. So please do join David on the 7th and David and I on the 14th for that live Q&A. And if you want more information about anything that we're doing here in terms of the school's work that we're trying to support, you can follow that link there that you can see on the screen, www.royalholloway.ac.uk. Follow that link through, type in geography, and you'll see a lovely growing list of resources. And we'll have far more about that in the new year. Follow us on Twitter, on YouTube, on Facebook, and we'll make sure that these lectures are made available to you so that you can follow them through, use them for revision, or embed them in your classroom teaching. So from Bethan and from me, thanks all very much for joining us. See you soon. Bye-bye.